transfer problem using ANSYS simulating software. So our problemer chosen the best heat transfer book by Cengel. So let's go to the problem. We previously choose here a problem, an example problem. So let's first read the problem here. So the problem was consider the flow of oil at 20 degrees Celsius in a 30 centimeter diameter pipeline and the average velocity is 2 meter per second. A 20 to 100 meter long section of pipeline passes through ice waters of the lake at 0 degrees Celsius. So we determine the temperature of the oil when the pipe leaves the lake. Let's simplify the problem. So here we see a pipeline here, and this pipeline is submerged in a lake, ice lake. So the inlet oil temperature is 20 degree with velocity 2 meter per second, and we find out here to outlet temperature. Also here given the upper and lower surface temperature of pipe is 0 degrees Celsius and the length of pipe is 200 meter. Also diameter is given 0.3 meter here. So let's go into our workbench. Okay. So previously I recorded a video, but my earphone microphone is turned off. That's why sound are not come here. But this time seems like okay. It takes two time here. Okay. So to solve our problem, we choose the ANSYS fluent flow application. So okay, fluid flow fluent. Okay, to easier our simulation, we choose a two-dimensional problem. So the pipe flow in respect to two dimension, we see a rectangle here, and the length is same as pipe length, 200 meter, and the width is equal to the diameter of the pipe is 0.3 meter. So let's draw the geometry first. Okay, so we enter design modular section. Okay, in XY plane, we look at me sketching and rectangle. So at first we draw a random rectangle, then we put down dimension here. So in dimension, the length is 200 meter, and the width is 0.3 meter. The width is equal to the diameter of pipe. So generate. So we need to concept through surface from sketches, then sketch 1, then apply, then generate. So here is our geometry here. So it's too long here. Okay, let's go into our meshing. So our geometry is too easy, a rectangular geometry. So it's not difficult to mesh here. It takes two time. Okay, it's come here. So here is our geometry here. You don't see properly. Okay, that's look like here. So normally in mesh, we element size we chosen is 100. So mouse are not working, so I change my mouse. Okay, then generate. So you use element size is 100 here. It takes two time. Basically, when you solve any kind of problem in ANSYS, so you need to reduce your element size because our precise result is required. Okay, let's also name our size. Here we see. Okay, also named my selection. Here is the surface of inlet. So we name selection. Named is inlet. So that is our inlet, and that is our wall. So we named selection, and it is our wall. Okay. Also the outlet is named here. Uh, that is our outlet. So we also named here as outlet. Okay. So all name selection is done here. So we see here is our inlet, here is our outlet, and here is our wall. Three name selection are given here. So we complete our meshing and update it. Okay, let's go dive into our crucial point is setup section. Here we put down our boundary condition and other models here. So we normally use in steady flow, so that's why we are chosen here display mesh after reading. But if you choose steady flow, then double precision must be okay. So we not use here double precision because our problem is steady. So start. Okay, here you see our problem geometry. Yes, that is our problem geometry here. So first we go into the general. So in general we are choosing steady, okay, then planar 2D space. And if you choose the gravity here, so you turn on the gravity option and choose the gravitational value here. So in our problem we are neglect the gravity section, so we turn off it. And in model section we are used in energy equation. Basically, fluent flow is normally used Navier-Stokes equation, normally continuity and momentum equation. But when the thermal effect R comes into our problem, then energy equation must be on. So in our simulation, a thermal effect must be okay. So that's why we turn on our energy equation. And viscous effect is laminar because in our problem we see the Reynolds number is less than 2000. Reynolds number is 666. So we know that in pipe flow, when the Reynolds number is less than 2000, the flow is laminar. So here we choose the flow model is laminar here. Okay. In material, so we need to build a material because the material is oil and it is not found in our fluent database. So the name is while, and the density also given here. We check the density. We check the density is 888, 888. So 888, Specific heat also given here, 1880. So specific heat 1880. Thermal conductivity also given 0.145. So we put down the thermal conductivity 0.145. Thermal conductivity is the crucial for transferring any heat transfer problem. So also viscosity given, and that is 0.901 10 inverse 6 probably. So check the value, 901 10 inverse 6. So it seems like okay, all the value are done here. So okay, close, then overwrite it, then close. Okay, the oil is put down here. Okay, so in cell zone condition sometimes it's automatically put down air, so we check out it. So in surface body, this is our fluid, and in edit section, okay, here you see the material name is air. So you must be check when you run your simulation the cell zone condition, because it's basically default air is put down. So we change our material from air to oil. Okay, that is okay. Let's dive into our important section is boundary condition. So let's check the problem. Okay, the boundary condition is given here. The inlet velocity is 2 meter per second, and the inlet temperature also 20 degrees Celsius. So let's put down the value. In inlet, the velocity is inlet velocity, and in edit section, we momentum is 2 meter per second, and the thermal condition is given 293. 20 plus 2073 and 293 is okay. At the outlet, we see the velocity outlet outflow normally, pressure velocity outlet, okay, and outflow. Okay, okay, outflow, and in wall the edit. Here you see the problem. The wall temperature, that means the upper and lower surface of the pipe, is 0 degrees Celsius. That means 273 Kelvin. So in thermal effect, temperature is 273. Uh, okay, okay. So our boundary condition is done. Here the mesh interface, these are not needed here. So in method section, so we normally use to solve our laminar problem is simple method. So we use simple here, and okay, and controls not needed. Initialization is hybrid initialization, and initialize our problem. Okay, the initialization was done. Okay, let's run the calculation here. Number of iteration, we choose 250 iteration. If you increase the iteration as your assumption, so you can change your iteration, because number of iteration when increase, the precision of result also increase. So we choose here 250. So run the calculation here. uh, it's solving now. Okay, calculation is completed. So let's check the result here. Okay, finally, it's contour, all domain, symmetry 1, and find the temperature here. So let's check the temperature. Okay, let's look like good. Okay, so here is our temperature contour. So we see the outlet velocity. So Let's check the result at outlet velocity. Okay, we need a probe. Let's say probe. এটা কাজই করতেছে না। দেখে okay, probe point. Probe টা এত কাজ করে না। কি হচ্ছে? এটা এখানে কাজ করছে না। Table viewer, viewer. Contour is also streamline contour. We see the symmetry 1 and velocity. Okay, this is our velocity streamline contour. So, but we need to temperature contour here. So that is our temperature contour, but my probe is not working. We need to check our temperature at outlet. So, well, এটা সরাই দেওয়া উচিত। Okay, that is our outlet. So let's check the value of outlet. কাজই করতেছে না। ওই জানে না। প্রবটা তো কাজ করতেছে না, কি করবো? দেখানো যায় না। তো ভিডিও পজ করে রাখছি আমি। So let's check the exit temperature here. So pause করেছি না? So here the probe and we check the exit temperature here. So 287. এটা কেন আসতেছে? আবার 287.